For this problem, we're asked to find a Thévenin equivalent circuit. Our opening move is to calculate the reactance of each component. Here's the reactance of the capacitor, and here's the reactance of the inductor. We can take these and then put the impedances on our schematic as negative J 26.5 and J 3.77 for the inductor. To calculate the Thévenin impedance, one of the things we do is we assume that that power supply is shorted. Keep in mind that when we conceptually short that power supply, we're also shorting out R1, so R1 does not exist. What we see then is from terminal A, we see the inductor, and then we see the resistor and the capacitor in parallel, yielding a Thévenin resistance of 8.8 plus J 0.5. Again, that 100 ohm resistor is not part of the equation because when we conceptually shorted the power supply, we took the resistor with it. You could think of that resistor as part of the power supply if it helps. We can calculate the Thévenin voltage using a voltage divider rule. Here we have the impedance of interest over the total impedance for the series circuit, all multiplied by the source, which yields a Thévenin voltage of 70.6 volts at an angle of 69 degrees. And you notice that I like to keep the impedances in rectangular form and the voltages in polar form. Again, polar being the form that you'd actually measure had you gone and used a meter. It also makes it a little bit easier to draw out the Thévenin circuit itself, as the Thévenin in rectangular form gives you the components directly. That's 8.8 real ohms resistance and J 0.47 as the inductor. And of course, as I mentioned already, if we used a meter, we would read about 71 volts in this particular system. One final step, let's calculate the actual value for that inductor. Here we use the reactance formula in reverse to solve for L. And it turns out that L is about 1.2 millihenries.